Welcome back to the deep dive. You sent us a fantastic set of sources on some pretty specialized corners of the C++ standard template library.
hmm
And our mission today is really to distill all of that into the essential knowledge you need for, competitive programming and just designing efficient algorithms.
Yeah, absolutely.
We are plunging into C++ container adapters. So if you've ever felt that standard containers like, say, vector or list just offer a bit too much freedom, this dive is definitely for you.
And that freedom is the key word.
We're going to be focusing on the stack, the queue, and the priority queue.
And the central insight here, and this is, I think, the most important thing to grasp, is that these structures are adapters. They're wrappers.
Wrappers, okay.
They're built on top of other containers that you already know, like std.dec or std.vector, but their entire purpose is to impose a restriction.
So you're limiting what you can do.
You are. You're taking this, this Swiss Army knife of a container and turning it into a scalpel. It limits how you can access or modify elements, but in a very specific, controlled way.
That feels counterintuitive, restriction being a feature.
It is. But that restriction is the most powerful thing about them because it guarantees a certain kind of clarity and efficiency for very specific tasks.
I love that frame. Restriction leads to efficiency. So we're going to unpack these big three, and for each one we'll ask not just what the rule is, but why that rule, that restriction is so critical, especially when we look at those complex challenges from platforms like Kattis.
Let's start at the beginning. Let's start with the stack.
Okay, the stack. So the fundamental rule is LIFO, last in, first out.
Great.
We all know the analogy, a stack of plates, a tower of Jenga blocks. You can only touch the one on top, the one you just put down.
The most recent.
But, let's go a bit deeper than the analogy. I can already use the std.vector and just decide to only use pushback and popback. That's all IFO. So why does C++ give us a whole separate std.stack adapter for that?
That is a crucial question, and it gets right to the heart of the adapter approach. The main reason is, well, it's safety and intent.
Intent.
By using std.stack, you are making an architectural promise. You're telling anyone who reads your code, including yourself 6 months from now, that only LIFO access is possible. It's a guarantee.
Okay, so if I just use a vector.
If you use a vector and just rely on convention, someone could accidentally call insert in the middle or access an element by its index, and that completely breaks the LIFO rule. The whole integrity of your data structure is gone.
And the adapter just prevents that.
It prevents that. It would be a compile time error. The adapter enforces discipline. It trades flexibility for integrity.
I see. So it's about making your code safer and clearer.
Precisely. Now, technically, the stack does this by only allowing elements to be added or removed from the top. And the operations reflect this perfectly. You have push to add to the top, pop to remove from the top.
And top, just to peek at what's up there.
Exactly, just to look at it without removing it.
So this brings us back to what you said at the beginning, the underlying container concept. The C++ standard stack usually uses a std.dec by default. What's the implication of that choice? Why a dec?
That choice of dec, which is a double-ended queue, is very strategic. It allows for constant time, or O1, performance for insertion and deletion at both ends.
Okay.
And since a stack only ever uses one end, the dec gives you really excellent, predictable speed for push and pop.
So what if I, the listener, decided to use a std.vector under the hood instead?
Well, you could. The LIFO rule would still be enforced by the adapter, but if that vector needed to dynamically resize itself...
When it runs out of capacity.
Exactly. You could suddenly get a much bigger performance hit when you push a new element, much bigger than you'd ever see with a deck. So understanding that underlying choice is what elevates your coding from just functional to truly optimized.
That's fascinating. So the adapter guarantees the behavior, the LIFO rule, but the underlying container you choose dictates the performance.
You've got it.
Okay, let's shift gears completely. Let's talk about the queue. If the stack was all about last in, first out, the queue is all about fairness, sequential order.
It's the FIFO principle, first in, first out.
The classic waiting line.
It is the canonical waiting line. The element that's been waiting the longest is the first one to get served, no exceptions.
So structurally, this must be different from a stack, right?
Oh, completely. It needs two distinct access points. Elements are added at one end, we call it the back, or the tail.
And removed from the other.
And removed from the complete opposite end, the front or the head. This dual-ended activity is what fundamentally separates it from a stack, which, as we said, only uses one end.
So that means our functions for just looking at elements also have to multiply. We don't just have top.
Right. Now you have front to see who's next in line to be removed, and you have back to see the newest person who just joined the line.
And push adds to the back while pop removes from the front. It's very intuitive.
Very.
So, if the stack's main job is managing things like function calls or parsing, the queue's job seems to be about systematic exploration, processing tasks based purely on arrival time.
Exactly right. When you think about real-world systems like network packets or tasks for a thread pool, strict sequential processing is often non-negotiable.
You can't let a packet cut in line.
You can, and the queue adapter enforces that order. It makes sure no element can jump the queue. And just like the stack, the standard C++ queue also defaults to using a std.dec underneath.
For the same reason, I assume. Efficient additions and removals at both ends.
For that exact same O1 efficiency at both the front and the back.
Okay, so we've covered LIFO and FIFO. The rules seem pretty strict. Now, let's introduce the rule breaker, the priority queue.
Yes. This is where we break that sacred FIFO rule entirely. I mean, it's still a queue, in the sense that items are waiting to be processed.
But their place in line isn't fixed.
Not at all. It implements a completely different service model.
And this is where it gets really interesting. The priority queue is basically VIP treatment. It doesn't care when you showed up. It only cares about how important you are.
That's a perfect way to put it. The distinguishing feature is that every element you add has some kind of priority associated with it. An implicit or explicit score.
And when it's time to serve someone?
The one with the highest priority gets served first. Period. It doesn't matter if it just arrived a millisecond ago.
So how does it manage that so efficiently? It can't be searching the whole list every single time. That would be slow.
It's not, and this is critical. A priority queue is usually implemented using a heap data structure. A heap provides a structural guarantee that finding and removing the highest priority element is extremely efficient. It's typically done in logarithmic time, O log n.
Which is way, way better than a linear search.
Oh, massively better. So, unlike the stack and queue, which are about controlling access points on a list, the priority queue is all about one thing: constantly and quickly retrieving the maximum value, or minimum, but we'll get to that.
And the operations are simple again, right? Like the stack.
Very streamlined. You use push to add an element, pop to remove the highest priority one, and top to peek at it. The adapter completely hides the messy details of rebalancing the heap underneath.
It just works.
It just works. You tell it the priority, it maintains the order for you, and that guarantee is non-negotiable for a ton of optimization algorithms.
Which is the perfect segue. This brings us to the application section.
Yeah.
We've covered the theory, the restrictions, but now we have to prove why it's all so valuable. Why should you, the listener, really care about these specific structures?
Because when you're faced with a complex problem, the right data structure is like an intellectual shortcut. It tells you exactly how to manage the state of your program. And the sources give us some fantastic examples.
Let's start with the standard queue. It's fundamental to computer science. Systematic searching. The source material mentions the slide puzzle problem. Why is a simple FIFO queue the absolute backbone of solving something like that?
Because to solve a slide puzzle, you need to find the shortest possible sequence of moves.
Right, the optimal solution.
To guarantee you find that shortest path, you have to use an algorithm called breadth first search, or BFS.
The BFS explores level by level.
Level by level. It checks all possible moves that are one step away before it even thinks about checking any moves that are 2 steps away. And the only data structure that strictly enforces this rule is the FIFO queue.
Oh, how does that work in practice?
When you process a state of the puzzle, you find all the next possible states, its neighbors, and you add them to the back of the queue. This ensures they are only looked at after every other state at the current level has been processed. The queue isn't just a convenience here, it's the mathematical guarantor of optimality for BFS.
That's a vital distinction. It's not just helpful, it's required for the guarantee.
Exactly.
Okay, now let's jump to the other end of the spectrum, the priority queue. This seems essential for problems where the state is constantly changing, and you always need to act on the best option available right now.
Absolutely. Think about optimization problems. The sources detail one called Kings of the Forest.
Kings of the forest.
Yes. And that problem is all about continuously picking the strongest available knight. You can't just loop through a list every single time to find the strongest.
Too slow.
Way too slow. You need a structure that, as soon as you add a new knight, automatically maintains the order of strength so you can instantly grab the top one. A priority queue is built for this. It gives you that O log n retrieval every single time.
And what about that bank closing problem? That sounded complex.
That's a fascinating one. It's a complex simulation of customers arriving and leaving a bank.
Hmm.
To model that efficiently, you have to keep track of the very next event that's going to happen in time. For that, you need a min priority queue.
Wait, a min priority queue. We've been talking about getting the highest value. How is this different?
That's a great point. By default, the C++ std.priority queue is a max heap. So top gives you the largest element. But for a simulation like bank closing, you're tracking time. You always want the event with the earliest timestamp to happen next.
You want the minimum value.
You want a minimum value, and you can easily invert the priority queue to be a min heap just by changing some of the underlying logic.
Yeah.
In the bank closing problem, using a min priority queue makes sure your algorithm always processes the event that's happening soonest. It's the whole optimization trick.
Wow. So the same basic structure, the heap, can solve both max value optimization and min time simulation just by flipping the comparison. That's incredible flexibility.
It is.
And these structures, they're not always used alone, are they? They're like tools in a toolbox. The sources mention the select group problem, which needs a stack and a set.
That's a very common combination. The stack is often used to manage a depth-first search, or DFS. That LIFO structure perfectly models moving forward into a problem and then backtracking out.
And the set.
The set is there to guarantee uniqueness, to make sure you don't process the same element twice. So the stack manages the order of the process, and the set manages the state.
They work together.
They work in tandem. And look at an even more complex example, the Jane Eyre problem. Simulating that scenario needs a priority queue to pick the best book or gift at any moment, but it also needs a sorted list, or maybe even two sorted lists, to manage the pool of available resources. The priority queue makes the decision, and the other structures feed it the options.
That really drives the point home. These restricted adapters aren't just academic toys. They're essential building blocks that map directly onto the constraints of really hard problems. You save mental energy and you save computational time by picking a structure that already enforces the rules you need.
And if we tie this all back to our initial idea, the structural clarity that these adapters provide is their biggest asset. Whether it's the FIFO queue guaranteeing you'll find the shortest path, or the priority queue ensuring you always have immediate access to the optimal choice, these structures prevent errors and guarantee efficiency precisely because they limit what you can do with the data.
That's a powerful summary. So to quickly recap our deep dive, we looked at the stack, which enforces LIFO, critical for managing context, for recursion. We covered the queue, strictly FIFO, the engine behind systematic exploration algorithms like BFS.
Right.
And finally, the priority queue, which retrieves based on internal priority, making it essential for optimization and complex simulations.
And that brings us to, I think, a really crucial final thought that we touched on earlier. Since these adapters are just interfaces, just wrappers sitting on top of other containers, their performance profile is totally dictated by what's underneath.
The underlying implementation.
The underlying implementation. For most cases, the default choices deck for a stacking queue, vector as a heap for a priority queue, are great. They're optimal. But I would really encourage you to explore this further. Think about the exceptions. What if you're building a stack on a system where the memory allocation for a deck is just prohibitively expensive for some reason? Knowing the precise performance differences between using a vector versus a list versus a deck to implement that same LIFO interface, that's where deep optimization truly begins.
So understanding that even when the LIFO or FIFO behavior is identical, the performance can subtly shift based on the engine underneath.
Yeah.
That's the real mastery of these tools.
That's it. You're not just using the tool, you're optimizing the engine.
Thank you for joining us for this deep dive into C++ container adapters. We hope you feel armed with the structural knowledge to go tackle your next big algorithmic challenge. We'll catch you on the next deep dive.